Good morning, class. Welcome to the absent physics teacher presentation. Through the wonders of technology, even though I am not here, I still am here. So, too bad for you, huh? Well, how about we just get this started so we can get it over with. Inflicting the pain while I'm not even here. Anyway. Let's pick up where we left off. We talked about friction yesterday. We talked about static friction. We talked about kinetic friction, how static is between objects that are not moving. It kind of prevents them from moving. And we talked about the kinetic friction, kinetic being motion. So when things are moving, that they are experiencing what's called kinetic friction. So again, the analogy of it's easier to keep something moving than it is to start it in motion. So, well, we're going to dive in a little bit deeper now to friction and what it is and what makes friction friction. So, if you can see on the board, hopefully, what we have is the first line says the amount of friction is directly proportional to the normal force. All right, remember normal force Fn. Now, for diagram's sake, all right, if I draw a little box up here at rest on the table, there's going to be two forces. All right, Fw, Fn, which if it's at rest, are both equal and opposite. So they cancel each other out. Now, if I add a downward force or downward push, the weight's not going to change, but the normal force will have to increase to make up for the added downward push. All right? Let's do some practical examples. Take your notebook, folder, whatever it is you have on your desk, and slide it around on your desk a little bit. All right, lightly moving it around. It slides nice and easy. The desks are nice and slippery. Now, take that same notebook and push down with it with your hand as hard as you can. Maybe not as hard as you can, but moderately hard. And now try to slide it around your desk. You'll notice that it is much more difficult to slide it because what we have done is we have increased the normal force, thereby increasing the friction. Okay? As Fn, as the normal force increases, friction also increases. So the heavier something is, the more friction force there is. That's why it's more difficult to move a piano than it is a keyboard. Okay. Now, friction also depends on surface type. Okay. So if I have two different surfaces, even though let's take a wooden floor that's really nice and smooth. Microscopically, there are a bunch of jagged edges on that wood, microscopically. And if you take something else that's nice and smooth, like say a piece of glass, microscopically, all right, there's going to be some rough edges as well. And it is the interaction of these surfaces here, 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 here that determine or create friction. Now, every surface has a different, or every material has a different surface. So there's going to be different amounts of friction depending on the material. So let's move ahead. Next slide. So each surface pair, glass, wood, rubber, and asphalt for tires, All right, sneakers and tile floor. All of these pairs have a measure called the coefficient of friction. All right, let me highlight that a little bit more. Yeah, coefficient of friction. Okay, coefficient of friction. Now this coefficient of friction is represented by the Greek letter mu, right there. Okay, mu is just kind of like the letter U, but with a leading tail. So, it's like a sweeping tail. So we have mu, all right, mu, mu. And this represents a value or a coefficient between two different surfaces. Okay, the lower the value of mu, the slipperier the surfaces are. So feet on ice, very slippery. Low mu. All right. The higher the mu, the stickier the surfaces are. All right. For lack of better terms, they stick together. Okay. So kind of like your face on a carpet. If you fall down and you fall on your face and you rub it against the carpet, that's a lot of friction. That's a high number of mu. Okay, so the subscript S and K, as you notice here, stand for static and kinetic. Now the equations are the same. All right, mu K is equal to the ratio of the friction divided by the normal. Okay, so it's actually kind of a ratio. This equation right here, this setup, is one that I recommend. All right, very popular, very easy to use. So all it's saying is that friction is equal to the mu, a predetermined value, times whatever the normal force is. So if you have a mu and you know the normal force, you can find out the friction that's going to take place. So let's do a quick review. We have a couple equations here that we've already been given. The first is Newton's second law equation. The sum of all my forces is equal to mass times acceleration. All right, that's equation number one. Equation number two, my weight is equal to mass times gravity. And actually, this is the acceleration due to gravity. So look, if you notice, ma, this is ma as well, but it's just the acceleration due to gravity. So force weight is equal to mass times gravity. And now the third equation to add to our list is F sub r, which is friction, is equal to mu, I'll write a K because that's the most common form of friction we'll deal with, mu K times Fn. All right. So these three equations really are the most, or the backbone of these problems that we're going to deal with. All right, so make sure you have those on your card at the very least in your notes. All right. Now, as I said before, different materials have different mu's. Take, for instance, steel on steel. All right, we have a static friction of 0.74 and a kinetic friction of 0.57. All right, and if you notice, all of these numbers are pretty high. 0.7 is pretty high. 1 is definitely very high. 0.9 is very high, glass on glass. You wouldn't think so, but it is. This column right here is higher than this column. Okay? So the static friction is always going to be larger than the kinetic friction because it takes more force to get something moving than it does to keep it moving. Okay? So you're not going to have to memorize any of these. You're not going to have to write any of them down. But do take note that most of these range from really low numbers, for instance 0.003, and this is in your joints, all right, like your shoulders or your hips, all right, very low friction, all the way up to 1 rubber on concrete. All right, think of automobiles driving on a road. Some of the roads are a concrete surface instead of an asphalt surface. Now, very rough surfaces, as they say down here, very rough surfaces occasionally can have a coefficient of over 1, but that's kind of rare. Again, you don't have to know these, and we're actually going to be able to use these a little bit later. So, without further ado, down here, watch this video. Teacher will cue it up and enjoy.